Hello and welcome to the Symposium. My name's Carl, and today I'm going to be talking about an introduction to logic, a sort of very quick beginner's guide to try and explain the terms that are used so you can understand a conversation that is happening regarding it. So logic is the study of reasoning in an attempt to answer the question, what makes the difference between good reasoning and bad? Logic itself is a normative subject, not descriptive. It asserts how we should reason. You begin with arguments, which is a sequence of sentences in the following formulation: the premises, followed by the conclusion. There are three types of logic that are most commonly used, the first being deductive logic, which is the systematic study of deductive validity. If the reasons given in an argument are true, then they guarantee the truth of the conclusion. Then we have inductive logic, which is how we make predictions about things we would otherwise need to be able to confirm with experience. It is how we infer B from A, even if B does not necessarily follow from A. And abductive logic is a logical inference about a set of circumstances that we have already observed, and we are using our inference to try and establish how this set of circumstances came about. So we're trying to establish A from B. This conclusion is not deductively valid, but what we consider to be the most likely explanation. We use all three of these forms of logic in our daily lives, but inductive and abductive logic is what we use more often, especially if you're, say, a parent and you've just walked into a room and you can see a mess. Well, you're going to use some abductive logic to blame it on your children. So an example of this, an example of a deductive argument would be, a formal argument would be, all rich people are happy. John is rich, and so we are forced to reach the conclusion that John is happy by the terms that have been laid out. An inductive argument, which is an informal argument, could be the potatoes have been boiling for 20 minutes, which suggests the conclusion that the potatoes are cooked. However, there might be reasons the potatoes weren't cooked. So the first argument is deductively valid. If we know the premises are true, which rich people are happy, and John is rich, then John must also be happy because he is also rich. The second example, by the way, money doesn't bring you happiness, so I point that out. There are a lot of very rich people who are very unhappy, but for the sake of the argument, for the sake of the example, we'll just take it as given. The second example is inductively strong. It is not deductively true that because potatoes have been boiling for 20 minutes that they are cooked. There could be extraneous factors that affect the duration required to cook potatoes. The water is not at a high enough temperature, the different kind of potatoes are normal, maybe you put like salt in the water and that changes the boiling temperature. Who knows what it is? However, common experience suggests that it's rational to conclude the potatoes are cooked even if it's not conclusively established. So what's the difference here? Well, the difference between validity and inductive strength is marked by whether the argument is monotonic. Deductive validity is monotonic. No matter how many premises are added to the premises of a deductively valid argument, the resulting argument is deductively valid. Inductive validity is non-monotonic. Other premises need to be added to the argument. Other premises that are added to the argument may reduce the inductive strength of it, which we can illustrate as following. For deductive reasoning, if we say premise 1, all rich people are happy. Premise 2, John is rich. Premise 3, being a lawyer is a bad way to get rich. And then we come to the conclusion, John is happy. Premise 3 doesn't really have a lot to do with the rest of the conversation, the rest of the argument that we're entertaining here. So even with premise 3, the argument is still deductively valid and guarantees John will be happy. The third premise is simply not relevant to the conclusion and doesn't affect the validity of premises 1 and 2. We can contrast this by further expanding the inductive, which is the non-monotonic argument, as follows. The potatoes have been boiling for 20 minutes, but premise 2 is that we're at 16,000 feet. And premise 3 is at 16,000 feet, water boils at a lower temperature. And so premise 4 is the cooking time is increased for water that is boiling at a temperature below 100 degrees. And so the conclusion, the potatoes are cooked, is an inductively weak argument. If the premises are all true, they fail to support the conclusion. There's probably, from what we've laid out there, probably extra time is required to cook potatoes at 16,000 feet. If we're climbing a mountain and stop at 16,000 feet to make dinner, the water we boil our potatoes in reaches boiling point at a lower temperature than at sea level. So our common experience of boiling potatoes for 20 minutes is not accurate due to other factors. It might even be shorter, I don't know. But we are not considering when we jump from premise 1 to the conclusion. So we have to consider these extraneous factors. That's not to say that is not to say that the potatoes cannot be cooked. There may be other premises we are not including in our reasoning, but with the information we have to hand, it's unlikely our potatoes will be cooked after 20 minutes. So, validity. Validity concerns the structure of the argument alone, and not the truth quality of the content of each premise in it. So, an initial intuitive definition of validity is an argument is valid if, necessarily, all the premises are true, and so is the conclusion. An inference is how we come to our conclusion. From the premises set out, presuming their truth, we infer the conclusion from them. There is also what is called patterning, which we must do in order to we must generalize in order to characterize validity. So patterning is essentially finding patterns in the sentences to understand the overall sentence structure and the structure of the argument that we're being given. So you can do this by identifying logical constants or logical connectives. In sentences, words like and or are logical connectives. The central role of patterning connects logic with algebra, and we work on how to pattern sentences because it leads to a deeper understanding of how the sentences themselves function. So we move on to first-order logic. So classical logic, otherwise called formal logic, or first-order logic with identity, or predicate calculus, has three components of any kind of logic. So, first-order logic. Classical logic, otherwise called formal logic, first-order logic with identity or predicate calculus, has three components. It has language, has the models for language, and has proofs in the language. In the language of classical logic, we find these primitive elements. So the first thing you start with are sentence letters. So these are usually called P, R, Q, etc. And these are our premises. Then you have sentence connectives, and they are and, or, if, and not, and they each have their own symbol, which I might put on the screen if I remember to edit this properly. Then you have individual constants, which are A, B, C, D usually used, and these are proper names, such as Mary, Peter, etc. Then you have a predicate constant, which is equals, which means identity or being the same as, or you can have greater or less than, which you know what they are. Then you have the predicate letters, which are the capitals F, G, H, or something along that area of the alphabet. Predicate letters describe a verb about the individual constants. So the individual constants being the proper names of things, and then the predicate letters describe what they're doing. For example, went home is a predicate of F, and John is an individual constant X. FX would mean went home John. Predicate letters are usually capitalized and start around F, G, H, I, something like that, and they describe a verb about individual constants, the individual constants being the proper names. So if we would say went home is predicate F, and John is individual constant A, then FA would mean went home John, or properly written in English, John went home. Then you get variables X, Y, and Z, all lowercase. Functioning the way pronouns sometimes do, as in the she, as if a girl is well read, then she is fun to talk to, can refer to things which are not proper names, such as groups, characteristics, pronouns, etc., etc. And then you have quantifiers, which are all and some. So using these components, the formulae of the language can be formed and used with precision. And now we get to me reading out formulas. So sum x, sum y, brackets, fx and gy and not x equals y. So that's really horribly complicated. I don't know how well that's going to translate, but if f is dog and g is cat, then we've got sum x, sum y, dog x and cat y, and not x is y. So if anyone has figured this out before I tell you what that means, do post in the comments. So essentially the formula says, some dogs and some cats exist. They are not the same, or there is at least one cat and one dog. There is definitely some ambiguity in that sentence, but an interesting fact about classical logic, which increases its appeal, is that it is sound and complete. And the soundness consists of the fact that anything provable, as in proof theoretically valid, is modal theoretically valid, and its completeness is in the fact that anything modal theoretically valid is provable. Because models and proofs are structures of very different kinds, their convergence is reassuring, encouragingly, rightly or wrongly in fact, encouraging the view that classical logic has locked on to at least a genuine feature of reasoning. And then we come to second-order logic. Now, it's got the same qualifiers as first-order logic, but it allows us to move from first-order logic to set theory with two additions, which are epsilon, which is a member of, and then some way of specifying sets. You can just list their numbers with curly brackets is the normal format. So if you would say a set of prime natural numbers less than 10 is curly brackets 1, 2, 3, 5, and 7. So you wouldn't need to write out the entire set if you had a set predetermined. Now, if you've ever done any sort of programming, this will probably come quite naturally to you, because it's one of those things like creating arrays and referencing arrays, or referencing a function that pulls something specific out of the array of whatever the command is. This is something you will have done naturally in programming. So it's not so terribly complicated as it sounds. Alternatively, you can describe a set using a set builder notation, which is the only practical approach for many sets with many members. So the set just given in the list fashion can be described in the set builder style in this way. So curly brackets x is a natural prime number that is less than 10. It can read the set of things x, such as x is a natural number less than 10. And this notation enables us to describe a set of members who cannot all be listed, because these sets could be very, very big. In second-order logic, there are quantifiers which bind predicate letters like F and G, so you get formulae like this. So you've got all F, some X, and then brackets Fx. So all F, comma, some X, then X does F. And if F is walk home, X could be people. For all walk home, for some people, people walk home. So to put that slightly more understandable, in a more understandable way, for the act of walking home, there are some people, and of this, some people walk home. So is this valid? Well, no. The formula states that every property, f or walking home, has an instance. All walking home is done by some people, and people walk home. It might be that nobody walks home, and so there is no instance of f, which is the walking home part. So that's not a valid sentence. Then we move on to quantified modal logic, which is an extension of first-order logic that has come to be important in philosophical logic. Quantified modal logic adds the box symbol, which is understood to express necessity. The reason for this is explained in this following example. So you've got the first-order formula, and the formula is for all x, x equals x. This is valid, so, I mean, it just makes sense, doesn't it? All of x, x is x. Doesn't mean much, but it's true. In quantified modal logic, necessity is understood to be a box, necessity. I'll just use necessity for the ease of reading out. Is understood in such a way that a formula like the following will also be valid. So, necessarily all x, x equals x. So necessarily all that is x, x equals x. And that's true again. Otherwise it's not x. So this properly read, necessarily for all x, x is identical to x, or necessarily x is self-identical. Variations on first-order logic may take the form not of additional notation, such as quantified modal logic adding necessarily, the box, but of an altered understanding of the existing notation. And two examples of this are paraconsistent logic and free logic. Paraconsistent logic has the same language, which is the same symbols and formation rules, as classical logic, but rejects the validity of the following argument, which is classically valid, which is known as explosion. And this is P, not P, therefore Q. So what this is a form of contradiction. So you either have P or not P, and if you find this contradiction, therefore whatever you want Q to be. This form of argument was known to medieval logicians as ex contradictione quodlibe, I think that is, but the translation from Latin is from a contradiction, infer what you like, and is now more commonly known as explosion. From the contradiction, anything follows. And this is actually an important thing if you're thinking about contemporary philosophy, how often this is used to springboard from one logical argument to something that sounds quite ridiculous, really. One reason for being interested in logic that do not validate explosion is that you might wish a database that contains something inconsistent, not thereby to contain every sentence whatsoever, and it would be nice if the inconsistency could remain localized. And then we move on to free logic. Free logic is the term for a variety of other logical systems that are united by the common rejection of one classically valid form of argument, which something a something, therefore some x, something x something. So a translation of that would be Fido barks, therefore some x, x barks. So Fido barks, and Fido is an x, so it must be true that some x bark and x is something that barks. However, this does not work when you use a negative action. This only works for positive actions. Pegasus does not exist, therefore some x does not exist. Pegasus does not exist, and Pegasus is an x, so it must be true that some x do not exist, also x does not exist. Sentential logic, occasionally called propositional logic, is a sub-language of classical logic. It is formulated in just sentence letters and sentence connectives, and does contain qualifiers, if, etc., or whatever, or predicate letters, making it broad and primitive. For example, it cannot discern anything in common, more in common between Mary dances and John runs than it can between Mary dances and there are more than 94 million miles between the Earth and the Sun. So what we've been discussing are modals. Modals for a logical language, which is the mathematical structure that offers the interpretation of the language. The model should give a clear meaning to every formula in the language, however, meaning itself is a fuzzy concept, and so to address this, each formula has to be considered within its own context, as in within the model in which it was created. This means the validity can be expressed precisely because it only happens within that model. The standard definition of a model is an argument is model theoretically valid if and only if every model in which all the premises are true is a model in which the conclusion is true. So, for example, explosion is classically valid, but not in other models such as second-order logic. For each model, each formula has a truth value, which is either true or false. And this is represented in model theory using the following two symbols, a T or an upside-down T, T meaning true and the upside-down T meaning untrue for the current model that's being considered. In first-order logic, a sentential language is an assignment of one or other of the two truth values to each sentence letter. For example, fx or Mary dances can assign a truth value to both Mary and dances. Truth values for complex formulae, as in those containing something other than just a single sentence letter, are computed according to rules. One rule for each sentence connective, with the requirement that every formula gets assigned just one truth value. Using M for any model using a sentential language, and F1, F2, etc. for arbitrary formula in the language, the rules are horrifically complicated. So, and, which is M assigns T to F1 and F2, if and only if M assigns T, which is true, to F1 and true to F2. Or, which is M assigns true to F1 or F2, if and only if M either assigns true to F1 or assigns true to F2. If is M assigns true to F1, if F1, then F2. If and only if M either assigns not true to F1 or assigns true to F2. And then not is M assigns true to not F1, if and only if M assigns not true to F1. Again, how useful that's going to be for anyone, including myself when I come to listen to this for my notes, is up in the air. But this means that the truth in the model is defined for every model and every formula of a sentential language. So P and Q, therefore P. This is a valid model that assigns truth to both P and Q. So proofs. A proof is a mathematical structure different to a model. It is a sequence of formulae that meets highly specific conditions based purely on the physical features of the formulae itself, which is their shape and form. The aim is that when these conditions are met, later formulae will intuitively follow from earlier formulae, which give rise to an alternative definition of validity. An argument is proof theoretically valid if there is a proof of the conclusion from the premises. Logical constants. Logical constants are features that do not change from model to model, and upon which the validity of the model rests. So these are the sentence connectives, which are and, not, if, and or, the identity sign, which is just equals, and the quantifiers, which are some or all. Sentence letters, individual constants, predicate letters, and variables may be assigned different things in different models. We don't necessarily know whether the list should be extended, and if so, how. Should we include the necessarily expression, or epsilon, which represents the set theoretical membership? If the only criterion is that some system of models gives an expression a constant interpretation, what's to stop there being a system of models that assigns a constant interpretation to London or dances, thus making these expressions logical constants? A standard view is that logical constants are characterized as expressions that introduce no special subject matter, as in they are topic neutral. They are therefore available to structure an argument on any topic and give substance to the suggestion that validity is a matter of structure. And we'll finish this part with a look at Aristotle's syllogisms, which are very, very simple forms of argument. So an early attempt at defining the forms of an argument was done by Aristotle in the 4th century BC. A syllogism is an argument with two premises and a conclusion. Syllogistic logic is limited by the fact that it only has two premises, and there are many good arguments with greater or fewer premises. It also handles and, or, and if poorly, despite their importance. So, an example of a syllogistic argument would be all F's are G's, all G's are H's, and all F's are H's as well. This is not necessarily an argument in and of itself, as F, G, and H are variables that need to be filled in with valid premises, but you can see how this is going to be done straight off the bat. All doctors are human beings. All human beings are rational animals, therefore all doctors are rational animals. And finally, we have the rules of inference. A rule of inference is a reasoning pattern consisting of some premises and some conclusions. If we believe the premises, a rule of inference tells us that we should also believe the conclusions. And this was observed by Aristotle as the structure of the argument, rather than the facts that are going through it.